In mathematics, a group scheme is a type of algebro-geometric object equipped with a composition law. Group schemes arise naturally as symmetries of schemes, and they generalize algebraic groups, in the sense that all algebraic groups have group scheme structure, but group schemes are not necessarily connected, smooth, or defined over a field. This extra generality allows one to study richer infinitesimal structures, and this can help one to understand and answer questions of arithmetic significance. The category of group schemes is somewhat better behaved than that of group varieties, since all homomorphisms have kernels, and there is a well-behaved deformation theory. Group schemes that are not algebraic groups play a significant role in arithmetic geometry and algebraic topology, since they come up in contexts of Galois representations and moduli problems. The initial development of the theory of group schemes was due to Alexander Grothendieck, Michel Reynaud and Michel de Mazur in the early 1960s. Definition: a group scheme is a group object in a category of schemes that has fiber products and some final object S. That is, it is an S-scheme G equipped with one of the equivalent sets of data, a triple of morphisms mu, G times SGG, SG, and iota, GG, satisfying the usual compatibilities of groups. A functor from schemes over S to the category of groups, such that composition with the forgetful functor to sets is equivalent to the presheaf corresponding to G under the Onoda embedding. A homomorphism of group schemes is a map of schemes that respects multiplication. This can be precisely phrased either by saying that a map F satisfies the equation F mu equals mu, or by saying that F is a natural transformation of functors from schemes to groups. A left action of a group scheme G on a scheme X is a morphism G times SXX that induces a left action of the group G on the set X for any S scheme T. Right actions are defined similarly. Any group scheme admits natural left and right actions on its underlying scheme by multiplication and conjugation. Conjugation is an action by automorphisms, i.e., it commutes with the group structure, and this induces linear actions on naturally derived objects, such as its Lie algebra, and the algebra of left-invariant differential operators. An S-group scheme G is commutative if the group G is an abelian group for all S schemes T. There are several other equivalent conditions, such as conjugation inducing a trivial action, or inversion map iota being a group scheme automorphism. Constructions: given a group G, one can form the constant group scheme GS. As a scheme, it is a disjoint union of copies of S, and by choosing an identification of these copies with elements of G, one can define the multiplication, unit, and inverse maps by transport of structure. As a functor, it takes any S scheme T to a product of copies of the group G, where the number of copies is equal to the number of connected components of T. GS is affine over S if and only if G is a finite group. However, one can take a projective limit of finite constant group schemes to get profinite group schemes, which appear in the study of fundamental groups and Galois representations or in the theory of the fundamental group scheme, and these are affine of infinite type. More generally, by taking a locally constant sheaf of groups on S, one obtains a locally constant group scheme, for which monodrome I on the base can induce non-trivial automorphisms on the fibers. The existence of fiber products of schemes allows one to make several constructions. Finite direct products of group schemes have a canonical group scheme structure. Given an action of one group scheme on another by automorphisms, one can form semi-direct products by following the usual set-theoretic construction. Kernels of group scheme homomorphisms are group schemes, by taking a fiber products over the unit map from the base. Base change sends group schemes to group schemes. Group schemes can be formed from smaller group schemes by taking restriction of scalars with respect to some morphism of base schemes. Although one needs finiteness conditions to be satisfied to ensure representability of the resulting functor, when this morphism is along a finite extension of fields, it is known as Weil restriction. For any abelian group A, one can form the corresponding diagonalizable group D, defined as a functor by setting D to be the set of abelian group homomorphisms from A to invertible global sections of OT for each S scheme T. If S is affine, D can be formed as the spectrum of a group ring. More generally, one can form groups of multiplicative type by letting A be a non-constant sheaf of abelian groups on S. For a subgroup scheme H of a group scheme G, the functor that takes an S scheme T to G, H is in general not a sheaf, and even its sheafification is in general not representable as a scheme. However, if H is finite, flat, and closed in G, then the quotient is representable, and admits a canonical left G action by translation. If the restriction of this action to H is trivial, then H is said to be normal, and the quotient scheme admits a natural group law. Representability holds in many other cases, such as when H is closed in G and both are affine. Examples: the multiplicative group GM has the punctured affine line as its underlying scheme, and as a functor, it sends an S scheme T to the multiplicative group of invertible global sections of the structure or sheaf. It can be described as the diagonalizable group D associated to the integers. Over an affine base such as spec A, it is the spectrum of the ring A, X, Y, which is also written A, X, X minus 1. The unit map is given by sending X to 1, multiplication is given by sending X to XX, and the inverse is given by sending X to X minus 1. Algebraic Tori form an important class of commutative group schemes, defined either by the property of being locally on S a product of copies of GM, or as groups of multiplicative type associated to finitely generated free abelian groups. The general linear group GLN is an affine algebraic variety that can be viewed as the multiplicative group of the n by n matrix ring variety. As a functor, it sends an S scheme T to the group of invertible n by n matrices whose entries are global sections of T, over an affine base. One can construct it as a quotient of a polynomial ring in n2 plus 1 variables by an ideal encoding the invertibility of the determinant. Alternatively, it can be constructed using two variables, with relations describing an ordered pair of mutually inverse matrices. For any positive integer n, the group μn is the kernel of the nth power map from Gm to itself. As a functor, it sends any S scheme T to the group of global sections f of T such that Fn equals 1. Over an affine base such as spec A, it is the spectrum of A, X. If n is not invertible in the base, then this scheme is not smooth. In particular, over a field of characteristic P, mu P is not smooth. The additive group GA has the affine line A1 as its underlying scheme. As a functor, it sends any S scheme T to the underlying additive group of global sections of the structure or sheaf. Over an affine base such as spec A, it is the spectrum of the polynomial ring A, X. The unit map is given by sending X to 0, the multiplication is given by sending X to 1x plus x1, and the inverse is given by sending X to minus x. If P equals 0 in S for some prime number P, then the taking of PTH powers induces an endomorphism of GA, and the kernel is the group scheme alpha P. As a scheme, it is isomorphic to mu P, but the group structures are different. Over an affine base such as spec A, it is the spectrum of A, X. The automorphism group of the affine line is isomorphic to the semi-direct product of GA by GM, where the additive group acts by translations, and the multiplicative group acts by dilations. The subgroup fixing a chosen base point is isomorphic to the multiplicative group, and taking the base point to be the identity of an additive group structure identifies GM with the automorphism group of GA. A smooth genus 1 curve with a marked point has a unique group scheme structure with that point as the identity. Unlike the previous positive dimensional examples, elliptic curves are projective. Basic properties. Suppose that G is a group scheme of finite type over a field K. Let G0 be the connected component of the identity, i.e., the maximal connected subgroup scheme. Then G is an extension of a finite étale group scheme by G0. G has a unique maximal reduced subscheme GRED, and if K is perfect, then GRED is a smooth group variety that is a subgroup scheme of G. The quotient scheme is the spectrum of a local ring of finite rank. Any affine group scheme is the spectrum of a commutative Hopf algebra. The multiplication, unit, and inverse maps of the group scheme are given by the commultiplication, counite, and antipode structures in the Hopf algebra. The unit and multiplication structures in the Hopf algebra are intrinsic to the underlying scheme. For an arbitrary group scheme G, the ring of global sections also has a commutative Hopf algebra structure, and by taking its spectrum, one obtains the maximal affine quotient group. Affine group varieties are known as linear algebraic groups, since they can be embedded as subgroups of general linear groups. Complete connected group schemes are in some sense opposite to affine group schemes, since the completeness implies all global sections are exactly those pulled back from the base, and in particular, they have no non-trivial maps to affine schemes. Any complete group variety is automatically commutative by an argument involving the action of conjugation on jet spaces of the identity. Complete group varieties are called abelian varieties. This generalizes to the notion of abelian scheme. A group scheme G over a base S is abelian if the structural morphism from G to S is proper and smooth as geometrically connected fibers. They are automatically projective, and they have many applications, e.g., in geometric class field theory and throughout algebraic geometry. A complete group scheme over a field need not be commutative, however. For example, any finite group scheme is complete. Finite flat group schemes. A group scheme G over a Noetherian scheme S is finite and flat if and only if OG is a locally free OS module of finite rank. The rank is a locally constant function on S, and is called the order of G. The order of a constant group scheme is equal to the order of the corresponding group, and in general, order behaves well with respect to base change and finite flat restriction of scalars. Among the finite flat group schemes, the constants form a special class, and over an algebraically closed field of characteristic 0. The category of finite groups is equivalent to the category of constant finite group schemes. Over bases with positive characteristic or more arithmetic structure, additional isomorphism types exist. For example, if 2 is invertible over the base, all group schemes of order 2 are constant, but over the two adic integers, mu2 is non-constant, because the special fiber isn't smooth. More detailed analysis of commutative finite flat group schemes over p-adic rings can be found in Raynaud's work on prolongations. Commutative finite flat group schemes often occur in nature as subgroup schemes of abelian and semi-abelian varieties, and in positive or mixed characteristic, they can capture a lot of information about the ambient variety. For example, the p-torsion of an elliptic curve in characteristic 0 is locally isomorphic to the constant elementary abelian group scheme of order p2, but over A, it is a finite flat group scheme of order p2 that has either p-connected components or one connected component. If we consider a family of elliptic curves, the p-torsion forms a finite flat group scheme over the parametrizing space, and the supersingular locus is where the fibers are connected. This merging of connected components can be studied in fine detail by passing from a modular scheme to a rigid analytic space, where supersingular points are replaced by disks of positive radius. Cartier duality. Cartier duality is a scheme-theoretic analog of Pontryagin duality. Given any finite flat commutative group scheme G over S, its Cartier dual is the group of characters defined as the functor that takes any S-scheme T to the abelian group of group scheme homomorphisms from the base change GT to GM, T and any map of S-schemes to the canonical map of character groups. This functor is representable by a finite flat S-group scheme, and Cartier duality forms an additive involutive anti-equivalence from the category of finite flat commutative S-group schemes to itself. If G is a constant commutative group scheme, then its Cartier dual is the diagonalizable group D, and vice versa. If S is affine, then the duality functor is given by the duality of the Hopf algebras of functions. The definition of Cartier dual extends usefully to much more general situations where the resulting functor on schemes is no longer represented as a group scheme. Common cases include FPPF sheaves of commutative groups over S, and complexes thereof. These more general geometric objects can be useful when one wants to work with categories that have good limit behavior. There are cases of intermediate abstraction, such as commutative algebraic groups over a field, where Cartier duality gives an anti-equivalence with commutative affine formal groups. So if G is the additive group GA, then its Cartier dual is the multiplicative formal group, and if G is a torus, then its Cartier dual is étale and torsion-free. For loop groups of tori, Cartier duality defines the tame symbol in local geometric class field theory. Lorman introduced a sheaf-theoretic Fourier transform for quasi-coherent modules over one motives that specializes to many of these equivalences. Example: the Cartier dual of the cyclic group of order n is the nth roots of unity. Dieudonné modules. Finite flat commutative group schemes over a perfect field K of positive characteristic P can be studied by transferring their geometric structure to a linear algebraic setting. The basic object is the Dieudonné ring D equals W, F, V, which is a quotient of the ring of non-commutative polynomials, with coefficients in Witt vectors of K. F and V are the Frobenius and Vichy-Bung operators, and they may act non-trivially on the Witt vectors. Dieudonné and Cartier constructed an anti-equivalence of categories between finite commutative group schemes over K of order a power of P, and modules over D with finite W length. The Dieudonné module functor in one direction is given by homomorphisms into the abelian sheaf CW of Witt covectors. This sheaf is more or less dual to the sheaf of Witt vectors, since it is constructed by taking a direct limit of finite length Witt vectors under successive Vichy-Bung maps V, Wn plus 1, and then completing. Many properties of commutative group schemes can be seen by examining the corresponding Dieudonné modules, e.g., connected P-group schemes correspond to D modules for which F is nilpotent, and étale group schemes correspond to modules for which F is an isomorphism. Dieudonné theory exists in a somewhat more general setting than finite flat groups over a field. Oder's 1967 thesis gave a connection between Dieudonné modules and the first RHAM cohomology of abelian varieties, and at about the same time, Grothendieck suggested that there should be a crystalline version of the theory that could be used to analyze P-divisible groups. Galois actions on the group schemes transfer through the equivalences of categories, and the associated deformation theory of Galois representations was used in Wiles's work on the Shimura-Taniyama conjecture.